So here's how these 9 days are going to play out, just kind of right now. So we'll finish up the energy stuff today. We'll review tomorrow, have that test on Wednesday. And then we need to do some thermodynamics, gas laws. That'll take a couple of days. And then that written final will be probably that last day on Thursday. So that's kind of what we're looking at as far as timing goes. So simply one test over energy, and then a comprehensive final that will cover everything. So, okay. So, anybody have any questions on that assignment? Kara?
No, I think I'm good.
Okay. Well, let's talk about number 10 and the importance of number 10. So, here's the Earth, here's the Moon, okay? So, kind of on a relative scale, Earth, okay, got this action going on. And you're trying to find the center of mass, okay? So, the easiest thing to do is let the position of the Earth just be 0, okay? Just say it's like we're going to start off and this is going to be 0. And then we're going to let the position of the Moon be that radius, okay? 3.84 times 10 to the 8th meters, okay? So then your formula is going to be, center of mass is going to equal position of the Earth times the mass of the Earth, you don't have to worry about, plus the mass of the Moon times this divided by the sum of both of those. And what you should get as an answer is something around like 5 times 10 to the 6th, okay? So that's where that center of mass is, which is actually inside the Earth itself, okay? Now here's the importance of that, is that in a larger scale, here's the sun, here's the Earth, here's the Moon. So what happens is the Earth, just that dynamic of the Earth and Moon, as that is orbiting around the sun, okay? So as that's happening, we're actually orbiting about that center of mass, okay? That center of mass is what's actually moving in a straight line. So because of the fact that center of mass is actually inside the Earth, so we wobble a little bit, okay, as we go around, not much, but if the Moon had been a lot bigger and that center of mass had actually been between the Earth and the Moon, like if it had been some point out in space, then that's what would actually travel in the circular path around the sun, and the Earth and Moon would be doing like this figure 8 thing where they would actually orbit around each other like this. But because of the fact that that position is actually inside the Earth, that's what allows us to have that stable orbit. And it's a good thing we have a Moon, because there's been any number of kind of theories that said if we didn't have a Moon, we probably wouldn't be here, because the Moon created tides, you know, even from an evolutionary standpoint. So by having tides, that allowed on the coastal regions that influx of fresh water all the time in and out. It stabilizes our orbit, okay, so we're not tilted as much as actually, you know, as to a certain extent has also absorbed some of the meteors that would have impacted the Earth, okay? So it's actually a good thing that we have the Moon. And if you want, some interesting theories about how the Moon actually came to be. There's some anomalies about the Moon, like the crust of the Moon that's facing the Earth is much thinner than the crust on the other side of the Moon, and so they're trying to explain that difference in the thickness of the crust. So anyway, on number 8, where you're finding the kinetic energies before and after, one kinetic energy should be around 2.5, and the other kinetic energy should be around 1.5. Okay, so what you're seeing there is that you're losing some of that kinetic energy in the collision. So when you have two objects that collide and move off, okay, that cannot be a perfectly elastic collision. Okay? all of your answers on number 4, and I wish I'd say I was clever when I wrote all these problems and I had this planned out, but I'm not. But all of your answers to number 4 should start with a 4. Okay? Every answer on number 4 should start with a 4. Okay? They're going to be different, but and this is going to be important once you get to today's assignment. So on C and D, on C you're finding that rotational kinetic energy, which should be around 4 times 10 to the third. Okay? So you're finding how much rotational kinetic energy that thing has as it's spinning. So that is going to equal to the work that was done to make that thing spin up to that. So your answers to 4C and 4D are the exact same, because the change in the rotational kinetic energy is equal to the work that was done. Okay? So both those answers are the same. And your answer to number 2 should be something times 10 to the 7th newtons. Okay? We're good? Going once? Twice? Sold. So get that handed in. All right, so here's kind of the last big summary thing. It really isn't anything new. We're just kind of take everything that we've learned and kind of sum it all together. So, is it possible for an object to have rotational kinetic energy and translational energy at the same time? Okay, is that possible to have rotational kinetic energy and translational kinetic energy at the same time? Matt, what would have to happen?
You should be rolling along the surface.
Yeah. So if I take, by the way, I hurt my wrist somehow. Oh, I know exactly what I was doing when I heard it. I don't know what happened to it. So I might have to get a phone call from the doctor's office, because like I'm okay if like this, but if I like try and do this, oh my God, levels of pain I haven't experienced before. So here I've got this wheel, right? So I can make it have just translational kinetic energy. So in other words, if I just take this thing, I just throw it, okay, without spinning it, that would just be, oh, how much kinetic energy does it have? The mass of the wheel times 1/2 mv squared, okay? That was it. So I can just have translational kinetic energy. I can also just make it have rotational kinetic energy, okay? So if I'm just making it spin and it's not going anywhere, then I just have rotational. But like Matt said, if I take this and I roll it along like this, then it's going to have both. It's going to have translational kinetic energy because it's moving. It's going to have rotational kinetic energy because of the fact that it's spinning. So every time you drive your car, each of your wheels on your car has both. It has translational kinetic energy because it's moving, and it has rotational kinetic energy because it's spinning, and has translational kinetic energy because it's going down the road. So, let's say that I have a 1 kilogram cylinder moves at meters per second. Okay. So here's the deal. So let's say I have 1 kilogram mass. How do I not have a 1 kilogram mass up here? Hold on, I need a visual. Huh? There it is. Like, I knew I always had one other. So we have 1 kilogram mass. Okay? And so this thing is rolling along like this at 1.8 meters per second. So I want to know the total amount of kinetic energy that it's going to have. So it's going to have some rotational and it's going to have some kinetic, right? So my total kinetic energy is going to be KT plus KR, right? Simple. Now here's the deal. The translational one is easy. That's just going to be 1/2 mv squared. I've got my mass, I've got my velocity, easy peasy, boom, we're done. Okay? Now, the rotational kinetic energy is a little bit more difficult, okay? Because what two things do you have to rotation, to calculate rotational kinetic energy? What do you multiply together to get rotational kinetic energy?
Moment of inertia and
I and
rotation.
butt squared. So you need the moment of inertia, and you need to know how fast it's spinning. So we got all the information for this side, okay? We got that. But we don't have this. We don't know the moment of inertia, and we don't know omega. It's like, hey, whoa, Bergkamp, you're trying to help us do this, and you haven't given us enough information. But let's just think this through, right? So, because it's a solid cylinder, Kara, how do you calculate the moment of inertia of a solid cylinder?
1/2 mR squared.
Okay, so this is going to be 1/2 mR squared. Okay? Now, this 1/2, okay, is different from this 1/2, okay? That's important. This 1/2 mR squared, this 1/2 exists because it's a solid cylinder, okay? If it was a thin hoop, this would just be mR squared. If it was a hollow sphere, it would be like 2/3 mR squared. So keep this 1/2, which is part of this, separate from this 1/2, which is part of the moment of inertia, okay? So keep that in mind. Now, you're going, okay, I've got the mass, all right, we got a 1 kilogram mass, but Bergkamp, you didn't give us the radius. Come on, man, you're killing us, you don't have the radius. All right, hold on. And you didn't give us omega either. So, but here's the deal. What's the relationship, and this is where you kind of got to go old school. What's the relationship between linear velocity and angular velocity? V equals what?
The omega.
R omega, right? V equals R butt. So if I solve for omega, I get V over R, right? So I'm going to take that and put that in here. So I'm going to have V squared over R squared. Okay, let's see where the magic takes us here. Okay, so I've got 1/2 mv squared. Now look what happens. I've got R squared here, but I've got R squared down here. So what's going to happen? This is a pirate's worst day. So what's going to happen to me R squared? I'm going to lose me R squared. Okay, it's bad enough that you lose an R. Oh, I'm losing me R squared. Okay, so those go away. So when I take a half times a half, check my math, I get 1/4 mv squared. So the reason that I didn't give you the radius is because you don't need it. Okay, the reason I didn't give you omega is because you don't need it as long as you know what your linear velocity is. Okay. So here's going to be the key substitution that you have to make in a problem like this, okay? Where you have butt squared, you need to put V squared over R squared. Okay, that's going to be the key substitution that you make in a problem like this. So Shivani, if I take 1/2 plus 1/4, what do I get?
3/4.
Beautiful. So I get 3/4 mR squared, or mv squared. So then I can go, okay, 3/4 times, Matt, you can take your calculator or somebody, times 1.8 meters per second squared. What do you get?
2.43.
2.43 joules. Okay? Now, so that's the total amount of energy that has. Now, if I wanted to, okay, if you wanted to just isolate how much like translational kinetic energy that you had, you could come back in here and go, okay, well, I could get this number, so I could take 1.8 squared times 1 times a half, and I could figure out just how much translational kinetic energy that I had. Then I could subtract that from the total and figure out how much rotational kinetic energy that I had. Okay, so if I wanted to separate them out, once I get this number, then I can subtract that from that and then get this number. Now, the other thing that I could do if I wanted to, if you wanted to figure out, well, just how fast is that thing spinning? So if you wanted to, and you'd actually have to have the radius at that point, if you actually wanted to figure out the omega, there's a couple of things that you could do. If I actually gave you the radius, then you could come in here and actually figure out omega, or once you figure out how much rotational kinetic energy that you have, set that equal to 1/2 I omega squared, and then you could figure that out from there. But at some point when you actually do the omega part, if you want to find the omega, or the actual moment of inertia, then you'd actually have to be given the radius. Okay, so, but here's what I want you to get out of this, is that when you have a problem like this, the most important substitution that you're going to do is where you put v squared over r squared for omega squared. Okay, that is the most important substitution that you're going to have. Okay, so I'm going to spin the camera over here and look at the problem over here. Actually, I'm going to work my way around. Okay, we'll start here. Okay, so here I've got one really strong magnet. Okay, so like even if I just put it there, it'll stay right there. So, is it possible when I'm move this thing up here, right? Okay. Now I'm going to turn this thing, and then I'm going to let it roll. Okay. So when it's up here, what's the only type of energy that it has?
Potential.
Potential. We have up, right? Okay. There's no springs. It's not moving. It's not spinning. It's only going to be up, right? Now, what I'm going to do is I'm going to turn it, and then I'm going to let it go. Now,
Do it again.
I will. Okay? So, when I let go of this thing, what happens to that up? What does it change into?
Kinetic energy.
Well, what types of kinetic energy?
Translational.
Translational and
Rotational.
okay, so here's the deal. So I've got up here, like let's say it's 2 joules of UG, right? So when I turn that and let go of it, it's going to roll down this hill. So that 2 joules of energy that I have here is going to get split. It's going to change into rotational kinetic energy and rotational and translational kinetic energy. Now, if I just hold it up like this, tough to do. Okay, if I just hold it up here and drop it, then it still has the same amount of UG, but if I just drop it, what is that? What's the only type of energy that it changes into? Translational. But if I put it up here where it can roll, it's going to change into both rotational and translational. Okay, so here's the point of the story. When you have UG, you can have both kinds. Yep, where it's uphill. You can let it roll and you can let it move down the hill. Okay, so with that said, so I've got yonder golf ball, okay? So there's 2 ways that yonder golf ball can get down the hill. Option number 1, I put it up here and I let it go, and I'm just going to let it roll down the hill, okay? Option number 2, I have it up here and I just drop it, okay? So here it rolls, here it falls. In both situations, what does it have in common? They both have translational, that is true. But what's the only one that has rotational? Yeah, when it rolls downhill like that. That's the only one that has rotational. There's also one very important thing that it has in common as well.
They both have the same, what are they called? MGH?
UG.
Yeah.
Beautiful. Okay, Shivani, it's a spot on observation. Okay? But so here's the deal. They both have the same amount of UG. Okay? So if I'm here and I drop it, So let's say that that's 1 joule of potential energy, okay? So if I have 1 joule of potential energy, when I drop it, all of that UG, that 1 joule, turns into nothing but translational. So if I have 1 joule here, it's going to land with 1 joule of energy there. But it's only going to be translational because it's not going to spin. So that's somewhat analogous to, let's say that you have a long lost aunt, okay? She has never had any kids and you're the only surviving heir. And let's say that she has $100,000, okay? She's going to say, hey, Kara, you're my only niece. I'm going to leave all the money to you. Kara's going, score, okay? So here's the $100,000. Kara gets all of it because it's all going to go to Kara. There's only one type of energy that it's going to change into, and that type of energy is what we're going to call Kara. Okay? So Kara gets all $100,000. Now, situation number 2. Kara has a brother. Okay, it's like,
Or a twin sister.
huh?
A twin sister.
A twin
That
sister.
sounds unrealistic here.
A sibling. How about that? Okay. So here's the deal. So there's still $100,000 to give away, but now it's going to get split. Okay. So are you going to end up with as much money?
No.
No. Okay. You might get $60,000 of it. Your brother might get $40,000 of it. Okay. But no matter what, you're not going to get all $100,000. So here's the story. On a problem like this, you're going to start with all UG, okay? It's all UG. Situation number 1, it falls, all of that UG turns into nothing but translational, okay? So mgh equals 1/2 mv squared, simplifies v equals the square root of 2gh. But if it rolls, it becomes much more complicated because now we have to split it between translational kinetic energy and rotational kinetic energy, okay? But here's what's going to be important. No matter what, you still start with the same amount of UG, okay? That hasn't changed. All right. All right. So here we go. Okay, so imagine this, that we're going to take Hank the bowling ball, okay, mass of 5 kilograms. And we're going to hold Hank up to a height of 0.2 meters, which is be about like yay, okay? And we're going to let Hank roll down the hill, okay? So we're going to start up there, have it roll down the hill. So when Hank gets to the bottom, here, what 2 types of energy is Hank going to have? Translational and rotational. So if you were to set up like a chart, okay, and embrace the chart. So you have a certain amount of UG, KR, KT, and then you're going to have the sum, right? So up at the top, what's the only thing that Hank has? UG, right? So that's just going to be MGH. We have no rotational, we have no kinetic. So whatever you have at the top is the total amount of energy that you're going to have at the bottom. So then, as you go across, if you can ever figure out what that UG is, everything has to add up to that same value, okay? Now, when it gets to the bottom, How much UG is he going to have? 0, because he has no height, right? Okay, he has no height, nothing. But what I do know is that the KR plus my KT has to add up to what?
MG.
Yeah, it has to add up to that MGH value, okay? All right, so because the energy has to be conserved. So here's what we're going to look at. We're going to look for that UG at the top equaling KT plus KR, okay? Because those two values at the bottom have to add up to the initial UG that we have at the top. So like Shivani said, that's going to be MGH. My KT is the easy part. That's going to be 1/2 mv squared. Now, the I omega squared, again, here's the tough part. I don't know I, and I don't know omega. Okay? Because you're going, Burkett, we can't do this problem. Yeah, we can. Okay? So this is why, especially on this, if you ever work with variables, this is the absolute case that you have to do this. You cannot work this problem by slamming numbers into this. You have to work this thing with variables, okay? So this is going to be 1/2 mv squared, 1/2. Now, because it's a solid sphere, moment of inertia is 2/5 mr squared, okay? If it had been a hollow sphere, it had been 2/3 mr squared. If it was a disk, it would have been 1/2 mr squared, okay? But because it's a solid sphere, we're going to have 2/5 mr squared. Okay? Now, we don't know omega, but this is where you do that same substitution again. You know, V equals R omega. So omega is V over R, and we're going to square that, so we're going to have V squared over R squared. Okay? So once we get this, okay, this is where the magic happens, right? So I've got MGH, 1/2 mv squared. Now, Miss Pfeiffer, when I take 1/2 times 2/5, what do I get?
I don't know, I'm bad at fractions.
Oh, sweetheart. I've got a 2 up here and a 2 down here. What can I do with these 2's?
Oh, cancer.
Yeah. So I just get 1/5, right? Now, let's continue with the fractions, Ms. Pfeiffer. I've got an R squared up here, but then an R squared down here. So this is the pirate's worst move, because what's going to happen?
Cancel.
Yeah, R, I'm going to lose me R squared. Okay? So those go away. So I got 1/2 mv squared. Now, Kara, I've got a mass, a mass, a mass. So what's going to happen to the mass?
Cancel.
Oh, I don't even have to have the mass. How cool is that? Okay? So Matt, I've got 1/2 v squared plus 1/5 v squared. So what do I get when I add those together? Well, what's the common multiple of 2 and 5?
7/10, right?
Yeah, so I got 5/10 plus,
I can add them
I can multiply, but like adding.
No, I
Because
can
then
write
I find the common denominator.
okay, the least common denominator 2 and 5 is
10.
10. So that's 5/10, right?
We understand.
It's
It's
just, I have to write it down.
Oh, I know. And then, so here's the whole point of the story, is that you get GH equals 7/10 V squared. So if you were to solve for V, you get the square root of
10/7 GH.
beautiful, 10/7 GH. Now, here's what I don't want you to do, okay? And I promise you, you're going to have a problem like this on the test. I promise you, okay? Here's the worst thing that you can do is say, oh, I'm just going to memorize this. V is going to equal the square root of 10/7 GH.
But
No.
that's first here.
Okay? This is only true if it is a solid sphere and the moment of inertia is 2/5 mr squared. If it was a hollow sphere like a tennis ball, that would be 2/3 mr squared. Okay? If it was a thin hoop, that would be mr squared. So the only thing that's true out of this whole process is everything but this. This is what changes everything depending upon the moment of inertia. Okay? This is what changes everything. Okay? So, in reality, what's the only thing I need to have to calculate this problem?
The height.
That's the only thing I need. I don't need the mass, I don't need the radius, I don't need anything. Okay? The only thing I need is the height. So Matt, we said the height was 0.2. So what do you get?
You get 1.67.
1.67 meters per second. Okay? So if you had like a radar gun, here's what that means. Is if you had a radar gun and as that ball was rolling towards you, okay, you would shine it, you would point that radar gun up, and you would see it and you would get a reading of 1.67 meters per second. Okay? That's what it would be reading. Okay? Go with this. Now, once you get this, then there's a couple of things that you could do. If you wanted to, you could actually calculate the MGH. So let's figure out how much energy we actually had to start with. So if we look at that UG value, which is going to be MGH, so Matt, take 5 kilograms times G times 0.20 meters.
9.8.
Is it really? Okay.
Yeah, because 0.2 times 5 is 1.
Yeah. So I got 9.8 joules, which is Kr plus my Kt. So here's what's happened. This is how much money Kara's aunt is going to leave. Okay? $9.8 million. Okay, let's dream big. Okay? 9.8 mil.
Kara.
Okay?
I wish I actually could have that.
Yeah, Kara's going, whoo, look at all my friends. Okay? I expect solar panels. Okay? That's all I have to say. I expect solar. Okay. So you got 9.8 million. Now, if she's the only child, so here's Kara, KR, right? No, actually this would be KT. This would be KT. Here's the deal. So visualize this. And this is going to be an important part. If Kara's the only child, Kara's going to get all 9.8. If she has a sibling, then that's going to get split. So if this is 9.8 joules, I can figure out how much translational energy that we're going to have. Because then I can go, okay, I got 9.8 joules, right? So if I were to calculate my translational energy, I'm going to go 1/2 mv squared. So Matt, take 1/2 times 5 kilograms times 1.67 meters per second squared.
$4.18.
Okay? So here's the deal. So I got 4.18 joules of translational kinetic energy. So if this is how much translational kinetic energy that I have, how can I figure out how much rotational kinetic energy that I have?
Simple.
Yeah, just subtract it. So this is 9.8 million. This is how much the sibling is going to get. So this is how much Kara is going to get, because Kara is spinning. Okay?
Oh, you got more than your sibling.
So, Matt, take 9.8 minus 4.18.
5.62.
5.62 joules. So that's how much rotational kinetic energy that there is. Okay? Now, from there, you can do a whole bunch of things. Like rotational kinetic energy is 1/2 I omega squared. So if you actually knew the radius, and you'd have to know the radius, then you could say, okay, then I could solve for omega. Okay? And you could figure out just how many radians per second it was actually spinning. So there's a whole bunch of things you can do once you get to that point. Now, here's what I want to do next. Instead of rolling, we're going to take that ball and we're just going to drop it. Okay, now before you do any calculations, when this thing was rolling, it ended up going 1.67 meters per second. If I just drop it and let it fall, when it hits the ground, do you think it's going to be going still 1.67 meters per second? Faster than 1.67 meters per second, or slower than 1.67 meters per second?
Fast,
Why?
because it has all the energy.
It has what?
Has all the potential energy converted.
Yeah. So all of that energy would go into translational, okay? It would all go there. So let's calculate that number. Okay, so we said UG now is just going to equal translational kinetic energy, okay? None of it's going to be lost to making it spin. So we can go, okay, that's easy. MGH equal 1/2 mv squared. The masses cancel out. You get the square root of 2gh is going to equal v. So this is if it all goes translational, okay? So, Matt, take 2 times g times 0.20 meters, and then the square root of that.
You get 1.99, 1.98.
1 point what?
98.
Okay, 1.98 meters per second. Notice that this is faster, okay? So if it just falls, it lands going faster than if you roll it and let it go down the hill. Matt?
Is this an average velocity?
No, that's that instantaneous velocity at the end. This is how
Okay.
fast it's going at the end,
Okay.
okay?
Got it.
Yeah, that is, the average would be, you'd have to know the time to find the average, okay? Or you could just divide it by 2, and if you're assuming that it has uniform acceleration, you could just divide it by 2 and go, oh, there's your average velocity, okay? So, now, here's what you cannot do, okay? Listen to me. Here's what you cannot do. If I ask you to find omega, okay, here's what you cannot do. You cannot go v equals r omega and use that as your velocity and then solve for omega, okay? Because here's the deal. This value here only exists if it's all rotational, if it's all translational. So you can't, here's on a problem like this is what you cannot do. You cannot solve it like this, where it's all translational, and then try and plug that into a rotational kinetic energy equation, okay? Nary the two shall meet. So you've got to take, this is the only time you can do this, is if you can take all of that energy and change it into pure translational. If it gets split up, you cannot use that step, okay? Cannot do that at all. Got it? Good? Grand? Okay. Okay, so yes, there's only 5 problems, but. So, now, let me give you the visual about number 2, okay? So, you're going to have a pendulum like this, okay? It's going to swing back and forth, okay? So, let me give you this visual. So, you're going to start off, listen to me. The pendulum is already moving at the beginning, okay? So, we're not starting it from rest. We're looking at it from the perspective that it's already moving, okay? So, it's already moving. So, what types of energy is it going to have because it's already moving? Kinetic and potential, because it's going to be above the ground, right? So it's like this. So listen to me. It's going to have kinetic and potential. Now, when it's at the very bottom of the arc, what's the only type of energy that it's going to have? Kinetic. So if it's up here, not moving, it's all potential. If it's down at the bottom, it's all kinetic. So in between, it's going to have both, right? So imagine this. This thing is already moving. It's going to swing down. Now, at the bottom, there's going to be a piece of clay. So it's going to hit this piece of play, and they're going to stick, and then they're going to move off together and swing up like this. So here's this visual. So this is going to tie in energy and momentum, okay? So you're here, right? It's already moving, both potential energy and kinetic. At the bottom, it's all kinetic, and then it's going to hit a piece of clay, and then it's going to swing up like this and stop. So what you're ultimately trying to find is the angle between the vertical and this string when it's at the top of this arc. Okay? That's your ultimate goal that you're going to try and find. Okay? Now, so on your sheet, you've got this handy-dandy equation that H equals L times 1 minus cosine theta. Thank you, dear.
You're welcome.
Beautiful. Thank you. So this is on your equation sheet. Okay, excuse me, this is on your sheet. If you need this on the test, I will give this to you. So what this is giving you is on a pendulum. So this L is the length of the string. Okay, so there's that. This is your angle theta. Okay, and this is obviously 1. So what it's giving you is the height of the bob above the ground. Okay? So it's above that equilibrium point. So clearly, the farther this goes out, the bigger this angle becomes and the bigger H becomes. Okay? So here's what you want to do first. So you're told that the length of this string is 1.5 meters. Okay? So you have this number. You've got an angle of 60 degrees. Okay? So you have that. So you've got 60 degrees. So you can figure out the H. You can figure out how high above the equilibrium point that is. So basically I kind of take you through this kind of step by step. But here's what's going to be important. Listen to me. It's already moving when you start this problem. It's already moving. So it's going to have UG and some initial kinetic energy, which is going to equal the final kinetic energy at the bottom. To get this UG, you've got to find this H to figure this out. Okay? Then you know how fast it's moving, so you can figure out this, and then you can find, oh, that's my final kinetic energy. Now, actually, if you work with variables on this problem, you'll see that it actually simplifies quite a bit down to a very recognizable equation. So if you're willing to work with variables first, it actually makes life much, much simpler at the end. Okay, now here's what's going to happen. It's going to hit down here, and then these two things are going to move off together. So one of the questions we're going to ask you is that what determines the potential energy that it has here? So what I want you to understand is that however much kinetic energy that I have here after the collision is equal to the potential energy that it's going to have up here at the top. Okay? So what you want to do eventually, your last step, is that you want to use this equation a second time. So you're going to know how much potential energy that it's going to have, because you're going to know how much kinetic energy that it has here. So you're going to know how much kinetic energy it has here is going to equal the potential energy up there, which is going to allow you to solve for H. Then you're still going to know the length of the pendulum. So what you have to do algebraically is isolate this cosine theta part and solve for this angle. If all goes well, this angle is in the mid-40s. Okay? So when you get done, if you work this thing and it's cool, this is going to be in the mid-40s. Now, let me give you a hint on one of these answers. So, because if 2C is wrong, everything else is going to be a train wreck. Okay? Your answer to 2C should be very, very close to 4 meters per second. Okay? Because if that is wrong, everything else is going to be wrong. Okay? Literally, everything else is going to be wrong. Okay? So your answer to 2C should be very, very close to 4 meters per second. Okay? If you don't get that, everything else, just stop. Do not keep working. Okay? You have done something wrong. So your answer to 2C is very, very close to 4 meters per second. Now, when you get to question number 4, okay? Number 4 is the satellite problem, okay? And it's going to tie together so many different things. So here's the deal on the satellite problem. So we've launched a satellite. And when satellites are launched, they're above, obviously, they're above our atmosphere. So you don't have the protection from UV rays and cosmic rays and things like that because it's out in space. So satellites are actually always being bombarded with some fairly nasty stuff. So one of the things that they want satellites to do, or spaceships in general, is what's known as a satellite, is what's known as a barbecue roll. So on a barbecue roll, what you want to do is you want to get this thing spinning so that one side isn't facing the sun, okay, and the other side is getting really, really cold. Because that's really, really tough on your satellite if one side's like smoking hot because it's in the direct sunlight and the other side is in the vacuum of space being really, really cold. So what you want to do is you want to get this thing into, and literally it's called a barbecue roll. So if you've ever seen like a rotisserie chicken where it spins very slowly so that you get an even heating on both sides, that's what you want to have happen on this. So what you want to do is you want to fire these engines to make this thing begin to spin at a certain rate. So if you look at what you're told, so here's this satellite, right? And you're going to fire these engines and you're going to make it go from rest up to spinning at 32 revolutions per minute. So right away, what are you going to have to do with the revolutions per minute? Change it into radians per second. 1 revolution, 2 pi radians. Okay? Divide that by 60. So you're going to start from rest, and you're going to make this thing speed up, where it's spinning at basically like 1 revolution every 2 seconds. Okay? So this isn't like warp speed kind of thing. Okay? You're making 1 revolution every 2 seconds. That way it's going to get an even heating all the way around. So, and again, if your answer to 4A is wrong, everything else is going to be wrong. So your answer to 4A, you have to calculate the angular acceleration. So your answer to 4A is going to be 0.01 and then something else. Okay? Because if that's wrong, everything is going to be wrong. Okay? Now, you eventually want to calculate the work that's done on this satellite to make it spin. Remember, work equals any change in energy. So what was the initial rotational kinetic energy of the satellite? Do not make this difficult. 0. It was at rest. So then you can find the final rotational kinetic energy. Oh, that's your change in your rotational kinetic energy. Guess what? That's going to be the work that was done. Now, you have to figure out how much fuel the rockets are going to take. Because this thing is equipped with 4 rockets that will spin. So imagine that you have these little rockets that will spin, that will fire to make them spin. So on 4C, you want to use the idea that force times time equals change in mass times your velocity. So what you're trying to figure out is how much mass you have to have. Now, on this one, I tell you that the rockets are expelling gas at 400 meters per second. So I'm giving you that value. You know time, you've got to figure out the force that's going to be required. So this is where you're going to go old school. So you've got to remember that torque equals force times radius, it equals I alpha. Okay? So to get the force, which you're going to find in part B, use that equation. Now, Once you get to G, you want to figure out the translational kinetic energy of this satellite as it's orbiting around the Earth. So on G, you have to find the velocity of the orbiting satellite. So you got to go old school orbital equations, okay? You're going to know the radius of the satellite's orbit. You're going to have the mass of the Earth, figure out the velocity. So on G, that answer is going to be 10 to the 11th joules, which is a lot, okay? 5 is like one that we just worked. Did you get it?
Yep.
So on 5, you've got a solid cylinder, and it's going to roll down a hill. So on number 5, start with the idea that UG is going to equal KR plus KT. Okay? Good luck. You're on your own.